Hello everyone, my name is Zhangxi Tan. I'm from the RIOS lab. Today I'm going to talk about PicoRio, an open source RISC-V small board computer to elevate the RISC-V software ecosystem. This is actually work inspired by the Raspberry Pi from the ARM world. And this is the logo of our system. We're actually heavily rooted from Berkeley and Tsinghua universities. We're picking the school colors and painting this logo. This is actually joint work with my colleague Lizzie Li and Professor Lin Zhang of Tsinghua and also Professor Dave Patterson. First, I'm going to talk about the RIOS. RIOS stands for RISC-V International Open Source Laboratory at TBSI,清华Berkeley Shenzhen Institute. We found the lab about November last year. The lab is led by Professor Dave Patterson. RIOS is a 5-year mission to help to raise the RISC-V ecosystem to the state of art. We're focusing primarily on Encore IP and software. It's a non-profit organization. We measure success based on technology transfer. We're building industry quality IPs without patent lawsuit. So TBSI is actually a joint venture by Tsinghua University and UC Berkeley. We started about 6 years ago, and around 2014. We're teaching RISC-V and also other graduate courses in technology engineering. So RIOS is actually geographically distributed lab with the majority of the engineers at TBSI. So why do we build PicoRio? There are really two reasons. First, it takes a lot more than the CPU itself just to build a full system. You need really invest in other Encore IPs in your SoCs. And there are many RISC-V CPUs, open source, but there are very few high quality Encore IPs out there. For example, the cache controllers, interconnect, graphics, and camera ISPs, and so on. And also, we really need an attractive open source platform so we can really try new hardware ideas at system levels. For example, if you want to study your security and the trusted execution, it's not just the process itself, but also your peripherals and your bus architectures. And also, if you really want to try some RISC-V hardware extensions, for example, the latest J extension, the JIT runtime, even vectors, you need a platform to play with. And the second reason is that the community really lacks of really affordable RISC-V hardware platform that can run lots of softwares. There are very few software-capable boards for long-tail developers. And we have seen many MCU-based boards, but there are very few Linux-capable boards at a very affordable cost. The developer would not necessarily want to spend about $1,000 for sci-fi boards just for software development of a new ISA. So we started this PicoRio open platform project. There are a couple of features. First one is independent maintained. RIOS will be the solo non-profit organizations that will be the gatekeeper of the PicoRio. RIOS will be responsible for architecture development, ensure compliance, and publish the final design. RIOS will work with design houses and partners to produce the PicoRio at volume, but PicoRio will be vendor agnostic. Of course, PicoRio will be open source from the SoC, from the package design, board design, and software running on top of it. We'll release the source code under BSD-like open source license, but there are a couple of exceptions. For example, foundry-related IPs and high-speed commercial IPs interfaces, those things are pretty hard to open. But gradually, RIOS are trying to build open source version of those IPs. And another important feature of PicoRio is high quality IPs. RIOS is working with membership companies to develop industry strength IPs with very good documentation. Each of the IPs will go through real tape-out, manufacturing, and verification. Of course, PicoRio will support modern software stack, means SMP Linux, and with managed language such as JavaScript and WebAssembly. And another feature of PicoRio is low cost and low power. It's targeting battery power devices initially, and also has a price point of similar to Raspberry Pi. This shows you the complete software stack we're thinking of running on top of our PicoRio hardware. So this is the very modern software stack. Down the bottom, we have a microkernel-like hypervisor that support a rich OS, support secure firmwares with verified boot, and also enclave and a simple secure enclave with a simple runtime. For the traditional OS and also rich OS, we're actually looking at Chromium OS. This is really because it's very interesting because of the Chrome browser applications is running on top of it. We're thinking Chrome browser is a very modern piece of software where it has lots of engines. You have the layout engines and the JavaScript engines and the WebAssembly engines just within the browser itself. And also Chrome is interesting to us is because there are also progressive web application support, which is very common for Android application. Also, there's a Google Store or Google Play in the Chrome support at this moment. So we're thinking if we can run the full-fledged Chrome, we'll have a very good software support for RISC-V. So there are 3 phases of PicoRio development. The first phase is PicoRio 1.0. We're expecting the board sample by the end of this year. Runs Linux, command line version of Chrome OS, and also another Linux Foundation project called EdgeX. The second phase will be PicoRio 2.0. We're adding a GPU support, partner with Imagination, and also run our own designed hypervisors and WebAssembly runtime. Phase 3 will be a little bit down the road. The primary feature is adding a little bit more CPU performance to make the PicoRio have the Chromebook-like performance. And also the goal is trying to have more and more RIOS developed open source IPs. So let me show you a little bit more detailed about PicoRio 1.0 SoC. This is the chip we call PICMI. PICMI SoC is actually manufactured in TSMC 28nm HPC Plus process. On the left-hand side, I'm showing you the die photo and also the floor plan of the major blocks in PICMI. The die size is about 4.3 millimeter by 3.4 millimeter. We're packaging the die in a FCC-SB package. We're running the whole die at 500 megahertz peak, but the different component can run different frequencies for lower power applications. From left to the right, you can see a very structured DDR5. That's the LP DDR4. That's a single channel 16-bit. And also you see a USB 3 block, which is also fairly big. And there are also 4 large red boxes that are marked as CPU 0 to CPU 3. They are RV64 CPU clusters. They're for general purpose computing. And also there's one small one we call RV32, which is a 32-bit CPUs in the center. That's only for always on and controls. And also you see the green one. It's the network on chip, which is fairly big as well. And also the majority of the chip is occupied by the L2 cache. So we have 512K banked L2 cache. So for the CPU clusters and also network on chip, they're pretty much open source. We developed on our own. But for memory and I/O interfaces, there are commercial IPs and closed source. So more details about the processor itself. So for 32-bit core, we call RV32. This is always on CPU, 32-bit for control only. So we use a very simple in-order issue 4-stage pipeline design, very classic design. It doesn't have any floating points, so just RV32 IMC. It does have a TCM and L1 cache. It does have a PMP security support. There are extensive clock gating inside the core. It is really because it's always on. We want to have the lowest power. The 64-bit cores, we call them ORV64. They're pretty much general purpose computing cores. There are 4 of them that are in cluster. They're a little bit longer pipeline with 5-stage single in order issue, but has an auto order completion feature. It has a branch predictor, also have MMU, so it means you can run full-fledged Linux on top of it. Still PMP security support as well. So hardware floating point, double precision floating point, has atomic operations support, AMOs, the cache and the NOC also support it. And this is actually very important to have the NOC open source because your AMO instructions will definitely matter with your NOC implementations. And for the 64-bit core, we also have a coherent L1 cache design and L1 data cache design, and and also 512K banked L2 cache. I think there are 8 banks in it. And also the 64-bit core is designed to have optional vector extension support. So you can really put in your own your own accelerators in it. Another feature I really want to highlight of this core design, they're really high quality implementations. First of all, they are silicon proven. We also have other commercial applications just based on the cores in other chips. And also, if you look at the R1 coherent scheme, coherent data cache design, when we design it, we'll also have a formal verification along with it. We plan to open source that formal verification as well. And if you look at the performance and also the power energy efficiency is really competitive at least compared to open source cores we have seen so far. So let's use an example of the 32-bit core where we can find a lot of open source cores and to compare against. So if you look at the ORV32, that's the core we have compared to like 4 or 3 popular RISC-V open source cores. ICR, that's one of the early open source implementations, considered very efficient, and Palpino is quite popular. They're risky and zero risky. We're running a benchmark, which is MBench. That's a very modern embedded benchmarks. We run all the programs we could, and this is kind of like the geometric mean of the result. If you compare to the performance running on ORV32, depends on the applications, right? But consistently, we're getting about 25 to 82% faster than the rest of the open source cores. If you also look at the power consumptions, if the whole chip is activated, is inactive, fully at load, the power consumption is about like 200 milliwatt. So we started the PicoRio software development as early as in January. We kick off the project late January. We start with porting Chrome OS and also the V8 JavaScript engine within the Chrome OS and Chrome browser to RISC-V. By the time of May, mid-May, we have roughly about like 500 Chrome OS package ported, and also we have our verified boot of the Chrome OS running in RISC-V. And at the end of July, we are able to get the Chrome OS kernel and along with the Chrome verified boot firmware running on PicoRio hardware in our FPGA. And also we open source the V8 JavaScript engine to the general public. So this is the link to the V8 engine. And also I want to highlight that if you're really interested in JavaScript engine V8 port, we actually have another talk called Unlocking JavaScript V8 on RISC-V in this forum. We basically talk about the details and technical details of the V8 porting process. So please feel free and look at that, check out that talk. Regarding open source effort, so first for the software projects, V8 is the first project we push to the public. Right now it's already a community effort. We have wiki, Slack channel, and also bi-weekly meetings open to the public. And so far we passed more than 94% of the standard V8 tests, which is about like 15,000 tests. And we're right now in the process of doing the upstream work. And also the other ones, the Google Chrome verified boot, we also put them on the website. And another one is the Google Chrome OS port. Right now we're working with the community, and also we're working with some independent Linux hackers. And our approach right now is trying to add support for Gentoo Linux first, but we're actually actively looking for participant. In terms of hardware, our goal is trying to get the CPU and also cache design, the interconnect open source by the end of this year. And then packaging design and PCB board and schematics following that. So all the documentation and source code will be available through the RIOS website, doc.rioslab.org. This slide shows you the open source hardware roadmap in different phases of PicoRio development. So for CPUs, on-chip network, cache controller, package design, board design, and software and firmwares are pretty much open since phase 1, since the very beginning. And a more challenging part will be with the IOs. Slow speed IOs will be a little bit easier. Over time, we can gradually replace with our own implementation. High-speed I/O and PHYs are the most challenging ones, but controller is possible at the end of the phase 3. And for basic analog I/Os, it takes some time to build, but it's plausible to have our own designed basic analog and basic I/Os at the end of phase 3. GPUs is not what we're focusing on, and it will be stayed with the closed source for the PicoRio project. In PicoRio, we're not only working with open source IPs, but also we're working with our industry partners on their commercial ecosystems. For example, our case of GPU system in PicoRio, we're working with Imagination Technologies. We're basically taking their Power VR ecosystem into the PicoRio. Imagination is one of the leading vendors of the GPU providers. Their GPUs, the Power VR GPUs, has been used by Apple iPhones before. We're using it in our open source PicoRio as well. In version 2.0, we integrate the complete Power VR graphics pipeline. We have video encode. We have a GPU, we have a camera ISP, and also a display controller that can upscale to 4K resolution. The GPU we have is a GPU with the Vulkan support and also OpenCL support. The hardware encode decoder H264, H265 for lower power applications. All the Power VR IPs are integrated with our RISC-V CPU in a single address space and shared memory. Putting everything together, this diagram shows the IP status for the first two versions of PicoRio. So we have partner IPs, GPUs primarily, and also a lot of open source IPs we developed on our own, and some closed source ones for memory interfaces. But also there are a lot of blue boxes, like there are IPs and peripherals we really like to have in our future version of PicoRio. And overall, we're looking for a board target power of less than 50 milliwatt at idle and less than 500 milliwatt at busy. If you compare this against the ARM-based Raspberry Pi, even to the first original version, this is significantly lower power, which is Raspberry Pi Zero at 800 milliwatt idle and 1.6 watt at load. So in conclusion, I think we're at a very good start, but we still need a lot of help to complete the 5-year mission. And we hope the PicoRio 1.0 platform will be finalized and be ready at the end of this year, and also getting more feedbacks and keep developing for the future versions. If you're really interested in this project and have time, can have resources to help us, please let me know and send an email to us. With that, I'd like to thank your attention. I will be happy to take questions.